Okay, so we'll be referring to both of these then to the screen in this. So this is, as you can see, the so it is an outline of every function. Linearity has not appeared here anywhere. So one function, multidimensional space, is here, multidimensional space there. There is no whatsoever speaking of linearity. What is worth adding, and now what else is to be added here is that what's so special about for linear operators, especially important, is what inputs will give you 0, and that's the kernel. Okay, let me scroll this up. Here's the definition. That is the kernel and the image, yes. So, so the definitions are then very short, as you can see, and unless you elaborate, then it's just too short in order to catch what's going on. So once again, the possible outputs, that's the image range, and this is the kernel is here. What's so special about it? Its kernel is well, how can I describe it? Is solutions to the equation f of x, or whatever v I was using here, is equal to 0. Okay, so a linear operator could take a variety of values. It's the same with four functions, but this is a special set that we're looking for. Solutions to the set of the solution set to this. What is it? It is a system of linear equations. So we're looking for the set of a special solution set to a very special kind of solutions of a system of linear equations. Okay, so so that is the difference. They live in different places. When you do planes, it is confusing because it's the dimension of the space is the same. Okay, and they are seemingly they are, especially in illustrations, they are side by side. This is the image. This is the kernel. But they're really very different, live in different places, serve very different purposes. But at the same time, they are interlinked in a very profound way, and that is given by this theorem over here, a corollary rather, this one. Okay, so the dimensions are complementary. So in dimension 2, it means that they add up to 2, and it means that there are not too many possibilities listed at the bottom, 0, 1, 2. As you can see there. So if kernel is small, the image is large, and vice versa. Okay, so in the multidimensional space, you can imagine how that's going to work out. So I'm not sure what else worth mentioning. This is pretty much the illustration of what was anything else. Image and kernel. So so finding the image is easy. I'm sorry, the kernel is easy because it is simply a system of linear equation. You solve it, you found it. So the solution set is the kernel. The image is more complicated because if you think about it, it's still a system of linear equations. Okay, that's what image is. So image, where is that? If I could put it. So the image is so solve fx is equal to b, but not for x, for b. Okay, so that's the idea of the image. To find all possible outputs. So some of them, if you can find for a given b, you can find x. Then that b belongs to the image. Otherwise, it does not. So there's more to it. We just had examples illustrated, such as in this picture. 2 by 2, m is 2, and that's why we were able to put both of them on the same plane, and that's the only reason. But you can see how the kernel is collapsing to the origin. So that's what f does. And at the same time, if you now step away from single line, you take the whole plane. Where does the plane ends up? It ends up in that line, the red line. That's the image. typical situation is when there are no projection collapses or anything like that. You end up with the whole codomain as the image. So that is not atypical unless there is an imbalance between the dimensions of n and m. So you can imagine that when n is smaller than m, then there is no way you can cover the whole thing. So for example, n is equal to 1, m is equal to 2. So it's a line taken to a plane. I mean, it's not going to cover the whole plane. And about vice versa, if your n is 2 and m is 1, there is no way you don't have a kernel, a large kernel, right? Because once again, you have to squeeze a two-dimensional space into one-dimensional space, so you cannot do it without collapsing. Okay, so that's once again the complementary dimensions. So what was the other question?
It was dealing with, you guys know what to do with direction vectors for asked to find one, or
Direction vectors for a straight line, I think. Well, that's the only case that we considered. So a direction vector of a straight line. And straight lines might appear in two ways: either the standard pre-calculus way, y equal mx plus b, or the symmetric general equation of ax plus by plus c equal to 0. So one or the other. Naturally, the second line is more general than the first. The first line is a special case of the second line, right? So you can just as well ignore it and then concentrate on the second one. So how do we find the direction vector? It's usually is read from I'm sorry. Yeah. Okay. So right. So well, this is my line. Okay. And then what we're looking for is usually not only the direction of direction vector of a straight line, but also a point. So from some point, which is 0 if it is available, if it passes through the origin. So this is what, let's call it D, you need to find, but you might need a point. Okay, so one way is to find a point, and that if you have anything available, such as c equal to 0, a special case you have ax plus by. What does it mean? It means that it passes through the origin through 0, 0. So then choose p to be that point because it's the simplest. Okay, so if it at all possible, choose the origin. Okay, and then how do I find a vector? Well, there are formulas there, but since we're not talking about that really, how to find a vector?
Basis vectors?
No. It really has nothing to do with basis vectors necessarily. How do we find a vector? How to find a line anyway? We need 2 points. So all you need to do is to find another point on the plane, on the line, and that will give you the vector. Okay, because the length of the vector doesn't matter, only direction does. So any point, as long as it's not that point P, will do. So especially when, once again, passing through the origin, finding such a point is easy because, once again, there are actually infinitely many of them. So you pick any x or any y, and it will give you, respectively, y or x, and that gives you for the answer. So say x equal 1, then y is equal to negative a over b, right? So, and that is your vector then. So then vector D is 1, negative a over b. But then again, if you start multiplying, then there are other options. Say, how about B negative A. Slightly more satisfying if you think about it, right? So because then you understand the well, first of all, that minus sign is that what assures cancellation, right? So you end up with that equation. So just in case for the original equation, that you don't have to do any computations whatsoever because the direction vector is kind of a generalization of the idea of the slope. So you take that, and m is the slope. So if I take m the slope, so what's the direction vector?
Negative m.
No, first of all, it's got to be a vector. What's the meaning of the slope? Rise of the run. So it's x or y or x. So if I progress 1 unit horizontally, then what? If I progress 1 unit horizontally, I progress by m vertically. So right there you have your answer. So which is certainly a special case. So if this is 1 and this is 2, so 1 is a special case of 2. So either way, you don't have to do computations, but once again, you can guess and then plug it in and make sure that it works out. But it's, for the most part, it is there are just infinitely many answers. So how many points can you choose on the line? Every single one of them works. Vectors, in either this way or that way, the length of the vector doesn't matter, except for it cannot be 0. Okay? So, okay, something else? Well, maybe you think about. I'm coming back to this problem from last time. Representations of linear operators by their matrices. So that's a big idea to remember, that it's really not a hard question at all. All you need to find is where the 2 or more basis vectors go. Okay, so that's the example. So the last example is probably the most complex that we have seen. It is we go with rotation, and then we trace the 2 basis vectors where they go, and that's what we did last time. And then those 2 vectors are written in the column form. These 2 columns form they form the matrix. Okay, so as you can see, we did E1. 1, 0, we did 2, 0, 1, and then we have 2 columns, and they're combined together like this. So this one goes here, the first row, and the other one, the second row, and this one goes over here. Okay? Why I brought it up again, I want to do examples slightly more complicated. Let's do 3 by 3. 2, 0, 0, 0, 0, negative 1, 0, 1, 0. Okay. A lot of zeros. And once again, it might be you might pick up that and do a spreadsheet and see where as I experimented before, when you do it with 2 dimensions, you can just experiment with them and see what's happening with different curves where they go under F. This is 3-dimensional. So to visualize is hard, right? So you literally, this is the 3-dimensional space, and it is transformed to another 3-dimensional space, right? So this is 3 by 3, so this F as a linear operator goes from R3 to R3. Okay. The only hope is that we are able to rely on that theorem, that there is really nothing happening here other than, or to begin with, at least to start our analysis, we try to see where our 3 basis vectors went, and this is where they went. So 1, 0, 0 went this way. 0, 1, 0 ended up here, and 0, 0, 1 over here. Okay, so then we start asking questions. What is happening? If I want to verbally describe, so you can visualize what's happening in your head, even though you cannot draw it probably. So what is happening? If you're looking at the very first column over there, what has happened? What's happened here? It's a stretch. So okay. So if we're looking at this, we describe it as how we stretch the vector, the basis vector, which is what, E1, right? E1 stretched by 2, by a factor of 2, and but that's just one vector. If we want to describe it in terms of then the whole thing also happens. The same thing happens to the x-axis. Right, so this x-axis, x, y, and z, what has happened? The y-axis did not go anywhere. I mean, the x-axis, I'm sorry, did not go anywhere because it's located in the exact same spot, but it has been stretched. Okay, so like this. So this is still the same but stretched. Okay, and then we're left with the two other x's. And we have here E2, E3. As you can see, it's not as simple. It's definitely not a stretch. So what do we do?
Kind of took like the y-axis and like put it in the direction of the z.
Okay, and that appears to be what has happened. I'm sorry. Yeah. Yes, that's right. Okay, and what about the other one? So once again, E2 has E1, E2, E3. So E1 has been stretched. Okay, E2, what happened to E2? It has become E3. Okay, what about E3? Flipped E2, right? So if you can imagine that, okay, so once again, E2 has become E3 and E3 has become negative E2. Okay, what are we talking about here? If you can visualize it in your head or otherwise. If you can draw it, that would be great. Well, one trick is to look at first of all to make sure that we have taken care of E1, and we know exactly what has happened to E1, and the answer is well, stretch. Okay, so then E1 is wherever E1 goes, it does not go. It has nothing to do with E2 or E3, and vice versa, right? So these zeros are very important. It means that there is no interaction between E1 on one hand and E2, E3 on the other hand. So everything what is happening to E1 is happening within the x-axis, and whatever is happening to E2, E3 is happening where? Where? What?
They're swapping places.
No. What? ZY plane, that's right. Right? Because we are not stepping off to anything that off that plane. Why? Because as you can see, because of those 4 zeros that I pointed out. Which means that we could, to understand what's happening, we could just throw out E1 and look at this YZ. Okay, and then we have those two vectors. One of them is this, E2, and we know that it will be here. So this is f of E2. It becomes E3, right? And what happens to E3? It becomes negative E2. So this is f of E3. Okay, so well, look at the picture. What has happened? No.
Rotation.
It is rotation, right? It is simply rotation. It is a rotation. E2 has rotated to E3 and E3 to negative E2. So that's the rotation one. Both of them carry out the same rotation, which means that the whole thing rotates, right? So nothing else can happen. In fact, so that's what we have discovered by examination, pretty much, in kind of a decomposition of what's happening. But we could have discovered that. That's the big discovery that we made. Could we see it in the matrix, in the original matrix? This rotation. Look, take a careful look at the original matrix.
If you just look at like the bottom.
That's right.
Bottom right.
This one. This is the familiar matrix of rotation of 2 by 2. When it's 2 by 2, that's what a rotation looks like. A rotation 90 degrees. Let's be clear here. It's about 90 degrees here. Okay, so and then we discovered that indeed it is really not by accident, but because everything is happening within the x-axis separately from a y-z axis plane. Then we just concentrate on what's left, and that is a little matrix here, 2 by 2. Why? Because we're talking about the y-z plane separately. So there we go. We recognize this matrix as a familiar 90 degrees matrix. If it was any kind of sine cosine, which is just a couple of lines above, right? You can imagine that matrix over here we inserted over there in the green square. Then we are in the same place. So okay, if we try to summarize, then the x-axis stretch and rotation. So rotation in this xz plane is this, and the x-axis is that way. So we're stretching this way, or we're stretching in both directions. Okay. In the meantime, there is a rotation 90 degrees. Okay. So if you can visualize it, it's pretty hard to draw, but if it is possible to decompose this way, then at least you can imagine. You can describe it with words, and you can also imagine other similar thing happening. And by that, for example, you can imagine that the same thing happening when the axes are not when it's all happening around different axes. Okay, so this is what in fact one way to describe it is stretch and turn. Both of them are actually along the x-axis. Along the x-axis we're stretching and we're rotating around the x-axis as well. Okay, so you can imagine the same happening around any axis, or not axis, but rather any line. You can do the same trick. Then you won't have as many zeros here, and you won't be able to guess the answer from like this by examination. So the answer is certainly analysis that we have had, and that is the eigenvectors, eigenvalues. So just to confirm that, let's do eigenvalue analysis of this matrix. So if I take the determinant of f minus lambda I3, okay, so then what is it? 2 minus lambda 0, 0, 0, minus lambda minus 1, 0, 0, minus lambda. That is my matrix. Okay, subtracting so minus lambda on the main diagonal. Okay, so now the determinant. Remember how we computed determinants. It's in 3 by 3. It's pretty large, but because of so many zeros, our decomposition is still valid, so that it makes our life easier. Out of those, remember, 3 determinants, we only need 1, and that's the 1. So long story short, it will be 2 minus lambda times the determinant of the matrix that we have left, minus lambda minus 1, 0 minus lambda. I'm sorry, I missed the 1 over there. So minus, no, it's 1, right? 1, 1, and okay. So as you can see, what we end up with is 2 minus lambda, and the determinant. This is 2 by 2 determinant. It is what is lambda squared plus 1. Okay. So what we discovered by examination, in fact, can be discovered through algebra. So we already know what to look for. So you see it? we find eigenvalues. The first eigenvalue is 2, right? So if we set this equal to 0, find lambda. Lambda is equal to 2 is the first eigenvalue. Here, these are no real eigenvalues. We know what that indication of when the polynomial is not irreducible, such as x squared plus 1. It cannot be further factored without using complex numbers. So which means that, well, it means we know what it is. It means rotation. Okay, so especially when specifically it's lambda squared plus 1, we have already seen it. So it tells us that there is a rotation in that particular plane. So you can imagine that that analysis at the bottom would be equally applicable to a matrix which is way more complicated than that. But the algebra will reveal what's going on in this manner. So once again, determining real eigenvalues will tell you stretches and in those directions. And if you do not have real eigenvalues, it means that you have a quadratic irreducible factor somewhere. That indicates rotation. Okay, so roughly like that. Negative eigenvalues also give you a flip. Okay, so so that's just an example of what happens in 3 by 3. You can imagine what's happening in high dimensions. The same analysis will apply. Okay, more questions? Vectors, eigenvalues, so the kernel image, representations of linear operators by matrices, linearity. I'm not sure we talked about that sufficiently. Linearity of linear operators. So apart from representing linear operators with matrices, that's very specific point of view on linear operators, and it only becomes specific because the basis is chosen for when both of these spaces are equipped with the standard basis. Then you have a matrix. If there are no bases, no matrix. But it doesn't mean that there is no function. There is function. There could be a function. All of this still applies. You can still have image. You can still have kernel. So what makes it linear? Remember that property that it preserves linear combinations. At its simplest, preservation of linear combination is motion. Okay, so motions preserve linear operations, meaning addition and scalar multiplication. So if I have added here, in this space I added 2 vectors. Under the transformation, they end up once again added together in the target space. Same with scalar multiplication. So that is linearity. And then on top of motions, you add stretches and flips. Okay, so rotation is motion, flip is motion, meaning when the distances do not change. That's what you would call motion, right? When you have stretches, then it is everything changes proportionally or disproportionately within the space. Something else? We have 10 minutes left. Well, if you don't have any other questions, then so it's at 3 o'clock. I will be in the office if you have questions to ask right before the test. Okay?
So our final's at 3 to 5, right?
Yes.